black hole's gravity is so extreme that escape velocity exceeds 299,79792 kilometers per second. A 2024 study in Physical Review Letters confirmed that even light's trajectory bends irreversibly past the event horizon. But your own body, right now, would be stretched into a stream of atoms long before reaching that point. This terrifying threshold was first calculated by Karl Schwarzschild from the trenches of World War I. He mailed his exact solution to Albert Einstein in 1915, astonishing a man who thought such math was impossible. What Schwarzschild discovered was a mathematical boundary embedded in the fabric of reality. At a specific distance from the mass, now called the Schwarzschild radius, the curvature of space-time becomes so extreme that the future light cone of any particle points inward. Every possible path leads toward the center. There is no direction that leads out. It took the physics community 50 years to fully accept what he had found. To understand why black holes trap light, you must first unlearn what you think you know about gravity. Isaac Newton, in his 1687 Principia Mathematica, described gravity as an invisible force pulling objects toward one another, a cosmic tug-of-war between masses. This framework gave us the concept of escape velocity, the speed a rocket needs to break free from Earth's gravitational grip. For our planet, that speed is about 11 kilometers per second. For the Sun, it is over 600 kilometers per second. But in 1783, an English clergyman named John Michell posed a radical question to the Royal Society of London. What if a star were so massive, so impossibly dense, that its escape velocity exceeded the speed of light itself? At the time, light was thought to be a stream of tiny corpuscles, so Michell reasoned gravity could slow them down. He called these hypothetical objects dark stars. Pierre-Simon Laplace independently reached the same conclusion in his 1796 book Exposition du Système du Monde. Then the 19th century arrived, and light was redefined as a wave. In 1801, Thomas Young performed his double-slit experiment, demonstrating that light behaved as a wave, not a stream of particles. Later, in 1865, James Clerk Maxwell unified electricity and magnetism into a single theory, showing that light was an electromagnetic wave traveling at a fixed speed through a medium. Waves were not particles. They did not slow down when gravity pulled on them. They simply propagated. The concept of a dark star, which relied on the particle theory of light, was abandoned. Laplace himself removed the passage from later editions of his book. There was a deeper problem, one that Michell and Laplace could not have solved. Newton's theory of gravity treated it as a force that acted instantaneously across any distance. It worked beautifully for planets and apples, but it had no mechanism for interacting with a wave of light. To explain how gravity could trap light, you needed a new framework, one that did not yet exist. That framework arrived with Albert Einstein's general theory of relativity, presented in November 1915, and published in full in 1916. Einstein did not treat gravity as a mysterious force that reaches across empty space. Instead, he proposed something far more radical: mass and energy warp. The very fabric of space-time around them, and objects simply follow the curves. A planet orbits a star not because it is pulled by an invisible string, but because it is traveling along the straightest possible path through a warped geometry. Imagine a bowling ball placed on a stretched rubber sheet. The sheet dips. Roll a marble near the bowling ball, and the marble follows the curve of the dip, spiraling inward. That is gravity in Einstein's universe, geometry, not magic. Karl Schwarzschild was the first person to solve Einstein's field equations for a single spherical mass. From the Russian front, he read Einstein's paper and began calculating. Einstein was stunned. Schwarzschild's solution revealed a critical boundary embedded in the math. At a specific distance from the mass, the curvature of space-time becomes so extreme that the escape velocity, the speed needed to break free, equals the speed of light. This distance is called the Schwarzschild radius, calculated by the formula rs2gm seq, where g is the gravitational constant, m is the mass of the object, and c is the speed of light. For a mass equal to our Sun, the Schwarzschild radius is about 3 kilometers. For Earth, it is about 9 millimeters. Compress any object within its own Schwarzschild radius, and you create a region of space-time from which nothing can return. This boundary is the event horizon. It is not a physical surface. You cannot touch it. But once you cross it, the geometry of space-time flips. Outside the horizon, you can move freely in any direction. Inside, all possible paths, every future light cone, point inward toward the center. Time itself becomes trapped. To an outside observer, an object falling toward the horizon appears to slow down, redden, and freeze forever at the edge. But from the perspective of the falling object, time ticks forward normally until it reaches the center. At the center lies the singularity. The equations predict a point of infinite density and zero volume, where the curvature of space-time becomes infinite and the laws of physics as we know them break down. Einstein himself hated this implication. He believed the singularity was a mathematical artifact, a sign that the equations were incomplete, not a real physical object. In 1939, he published a paper in the Annals of Mathematics, arguing that physical processes would prevent the formation of black holes. He was wrong. For decades, most physicists treated Schwarzschild's solution as a mathematical curiosity. They assumed that real stars would never collapse to such an extreme state. In 1931, a young Indian-American astrophysicist named Subramanian Chandrasekhar calculated that a white dwarf star, the remnant of a dead star, could not exceed about 1/4 times the mass of the Sun without collapsing further under its own gravity. This became the Chandrasekhar limit. If a stellar core exceeds this mass, electron degeneracy pressure, the quantum mechanical force holding white dwarfs up, is overwhelmed. The core must collapse. Chandrasekhar presented his findings at a meeting of the Royal Astronomical Society in 1935. Arthur Eddington, the most eminent astrophysicist of the era, publicly ridiculed him. Eddington argued that some unknown mechanism would prevent the collapse. Chandrasekhar was humiliated. He left England for the University of Chicago, where he continued his work in relative obscurity. He would eventually win the Nobel Prize in 1983 for his work on stellar structure, but the wound from that 1935 debate never fully healed. 4 years later, in 1939, J. Robert Oppenheimer and his graduate student Hartland Snyder published a paper in Physical Review titled On Continued Gravitational Contraction. They took Chandrasekhar's logic to its final conclusion. If a star's core exceeds the limit, no force, not electron degeneracy, not neutron degeneracy, nothing can halt the collapse. The star shrinks past its own Schwarzschild radius. At that moment, the star becomes causally disconnected from the universe. No signal, no light, no information can escape. Time itself, from an outside perspective, appears to stop at the boundary. Oppenheimer and Snyder had described the formation of what we now call a black hole, though they called it a frozen star. The paper was mathematically rigorous and physically inevitable, but the world was about to change. Oppenheimer was recruited to lead the Manhattan Project later that year. Black hole physics was abandoned for nearly 2 decades. The silence broke in 1965. Roger Penrose, a mathematical physicist at Birkbeck College in London, published a paper that changed everything. He proved that under certain conditions, such as the presence of a trapped surface, a singularity is an inevitable consequence of gravitational collapse under general relativity. Penrose used a novel technique called topological analysis, showing that once a trapped surface forms, the collapse must continue inexorably to a singularity. Einstein had believed that singularities were artifacts of symmetry, that a real star would never collapse to a perfect point. Penrose proved him wrong. For this work, Penrose was awarded half of the 2020 Nobel Prize in Physics for the discovery that black hole formation is a robust prediction of the general theory of relativity. 2 years later, in 1967, John Archibald Wheeler stood before an audience at the NASA Goddard Institute for Space Studies in New York. He was tired of the cumbersome phrase, gravitationally completely collapsed star. During the lecture, he simply said, black hole. The name captured the imagination instantly. It was stark, final, and scientifically precise. A hole because nothing returns. Black because no light escapes. Wheeler did not discover black holes, but he gave them their identity. The term spread through the physics community within months. By the end of 1967, black holes were no longer theoretical curiosities. They were recognized as real astrophysical objects that must exist in the universe. The search for observational evidence began in earnest. The first strong candidate, Cygnus X1, was identified just 4 years later in 1971. The age of black hole astronomy had begun. Stephen Hawking sat in his office at Cambridge University in 1974, staring at an equation that contradicted everything he believed. He had just combined quantum mechanics with general relativity, two theories that were never meant to coexist, and the result was devastating. According to his calculation, black holes are not eternal prisons. They emit radiation. They glow, and eventually they evaporate entirely, vanishing from the universe in a burst of energy. He called it Hawking radiation, and it rewrote the definition of a black hole overnight. The mechanism is purely quantum. Near the event horizon, pairs of virtual particles constantly pop into existence and annihilate each other. Normally, this happens everywhere in empty space, and the particles cancel out instantly. But at the horizon, something strange occurs. One particle falls into the black hole, while its partner escapes into the universe. The escaping particle becomes real, carrying away a tiny fraction of the black hole's mass. Over time, billions of years for a stellar mass black hole, far longer for a supermassive one, the black hole shrinks, radiates, and finally disappears. A black hole is not black. It is the faintest possible glow. A thermal whisper at 60 nanokelvins for a solar mass hole, far colder than the cosmic microwave background that fills all of space. But Hawking's discovery opened a wound in physics that has not healed. His equations suggested that the radiation carries no information about what fell into the black hole. If you drop a piano into a black hole, the Hawking radiation that eventually escapes is random thermal noise. It contains no record of the piano, its composition, or its quantum state. When the black hole evaporates completely, all that information is lost forever. This violates a sacred principle of quantum mechanics called unitarity. Information cannot be destroyed. The universe must preserve a complete record of every quantum interaction, from the birth of a star to the collapse of a wave function. Hawking had just claimed that black holes break this rule. The black hole information paradox was born. Stephen Hawking insisted that information was genuinely lost, that quantum mechanics would have to be modified. Leonard Susskind, a theoretical physicist at Stanford, disagreed. He argued that information must be preserved, even if it means black holes are far stranger than anyone imagined. The debate lasted 3 decades. Susskind called it the Black Hole War. In 1997, Hawking made a public bet with John Preskill, another Caltech physicist, wagering that information was lost forever. In 2004, Hawking conceded the bet. Admitting that his own calculations had been incomplete, he presented Preskill with a baseball encyclopedia, the winner's choice of reference work for the information that had supposedly been lost. Then came the images. On April 10, 2019, the Event Horizon Telescope collaboration released the first direct photograph of a black hole's shadow. The target was M87, a supermassive black hole at the center of the galaxy, Messier 87, 55 million light-years from Earth. Its mass is 6 billion suns. Its event horizon is larger than the orbit of Pluto. The image shows a dark central region, the shadow of the singularity, surrounded by a glowing ring of superheated plasma moving at near light speeds. The ring is lopsided because the plasma is rotating, dragged by the black hole's immense gravity. The image matched the predictions of general relativity with stunning precision. Einstein was right again. 3 years later, in May 2022, the ET released a second image, Sagittarius A, the supermassive black hole at the center of our own Milky Way galaxy. Its mass is 4.1 million solar masses, far smaller than M87 but much closer, just 26,000 light-years away. Imaging Sagittarius A was far more difficult because its size changes rapidly over minutes, while M87 remained stable for days. The team had to develop new algorithms to average thousands of snapshots into a single coherent picture. The result confirmed that black holes are not rare anomalies. They are common. They sit at the center of most large galaxies, including our own, and they play a fundamental role in how galaxies form, evolve, and die. The black hole forces us to confront the limits of knowledge. At the singularity, general relativity breaks down. At the event horizon, quantum mechanics and relativity collide in ways we do not fully understand. The black hole, once a mathematical curiosity, has become the laboratory for the next revolution in physics. The answer to the information paradox may reveal the fundamental nature of reality itself. The universe is not only stranger than we suppose, it is stranger than we can suppose.